Thermochemistry 2, Part 2, Entropy and the Second Law of Thermodynamics. Specifically today we're going to be looking at the Second Law of Thermodynamics, the effect of temperature on spontaneity, calculating entropy changes in chemical reactions, standard state entropies, and then finally some practice calculating entropy changes. Entropy and the Second Law of Thermodynamics. In any spontaneous process, there is always an increase in the entropy of the universe. Or in other words, the entropy of the universe is increasing. For a given change to be spontaneous, the entropy of the universe must be positive. So the relationship for a spontaneous reaction to occur between the change in entropy of our system and the change of entropy of our surroundings must work together to give us an overall positive value for the change of entropy in the universe. The effect of temperature on spontaneity, direction of heat flow. Entropy changes in the surrounding are primarily determined by heat flow. Exothermic reactions in a system at a constant temperature will increase the entropy of the surroundings. This will happen by releasing energy, as we see that this is an exothermic reaction. An endothermic reaction in a system at a constant temperature will decrease the entropy of the surroundings as it absorbs energy from the surroundings into the system. As a result, the surroundings become more organized and the entropy decreases. The magnitude of the increase in the entropy of the surroundings due to the dispersal of energy into the surroundings is temperature dependent. The greater the temperature, the smaller the increase in entropy for a given amount of energy dispersed into the surroundings. Now remember, entropy is a measure of energy dispersal in joules per unit temperature. The higher the temperature, the lower the amount of entropy dispersed. Let's relate that to an example. If 1,000 joules of energy is released onto hot surroundings, the entropy increase is small, because the impact of 1,000 joules is small on the surroundings that already contain a lot of energy. If 1,000 joules of energy is released into cold surroundings, the entropy increase is large because the impact of 1,000 joules is great on the surroundings that contain little energy. Now let's relate that to you. In this first example, let's imagine that someone who is very, very wealthy suddenly receives $1,000. That $1,000 probably doesn't mean that much to a very, very wealthy person. But if I take that same $1,000 and I give it to someone who is not so wealthy, maybe a senior in high school that's going on to college, that's going to have a lot of student debt, well, that $1,000 will mean a lot more. It'll have a greater impact on that student going into college than the wealthy person that already has a lot of money. So we can take that analogy and relate it to 1,000 joules of energy being released into hot surroundings, not much of an impact, versus 1,000 joules of energy released into cold surroundings where you'll see much more of an impact. Entropy changes in chemical reactions. Measuring a change in entropy for a reaction is pretty complex. The absolute value of entropy S for many substances at any temperature can be done by measuring variations of heat capacity with temperature. Entropies are usually tabulated as molar quantities in units of joules per mole Kelvin, otherwise represented as these symbols right here. Standard state entropies. The molar entropy values of a substance in their standard states, denoted as S naught. The entropy change in a chemical reaction equals the sum of the entropies of the products minus the sum of the entropies of the reactants. And oh my, doesn't this look familiar? For many of you, you might be recalling something like, Hess's law. So this format right here, this setup is going to be very, very similar to what we did with change in enthalpy, heat changes using Hess's law, where the change in entropy at standard state is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. Let's do a bunch of examples to remind ourselves how this works. Using the standard entropy values that are found at the back of your textbook, calculate the standard entropy change delta S naught for the following reactions at 298 K. So here's my chemical reaction. I have aluminum oxide plus hydrogen gas yields solid aluminum and water as water vapor. So the way that we're going to set this up is we're going to do delta S naught is equal to the sum of the products. Now the products is this 2 moles of solid aluminum. So I'm going to put Al as a solid plus 3 moles of water in the gaseous state. And we want to make sure that we pay really close attention to those states of matter here because they're going to be different entropy values for different states. Minus the sum of the reactants. So I'm going to have 1 mole of Al2O3 as a solid plus 3 moles of hydrogen gas. Now the next thing I'm going to do is go to the tables that are in the back of my textbook and look up the entropy values associated with each one of these products and reactants and fill them in. So here I have my entropy values filled in for each one of my reactants and products. So my value for aluminum solid is 28.32 plus my 3 moles of water in the gaseous state, which the entropy value is 188.8, minus my reactants, 1 mole of my Al2O3, which is represented as 50.9, plus my 3 moles of hydrogen gas, which is represented as 130.7. Now what I'm going to do is go through the process of multiplying, adding, and subtracting to find my overall delta S value. I find that when I take my products and I multiply and I add them together, I get 623.04 minus 443, which represents my reactants multiplied and added together. This will give me a final value of 180.04 joules per mole Kelvin. Let's try another one. C2H4 plus H2 yields C2H6. Let's start out by writing out our formula to find our overall delta S in the standard state. So what I've done here is I've done, again, products minus reactants, where I have 1 mole of my C2H6 minus 1 mole of my C2H4 plus 1 mole of my H2. The next thing that I'm going to do is go to the tables and fill in the values for all of my compounds. So for C2H6 in the standard state, the value associated with this for entropy is 229.2. For C2H4, my first reactant, it's 219.3. And for H2, it's 130.7. So now what I've done is basically said 1 times 229.2, which I have down here, minus, I have my 1 mole times 219.3 plus my 1 mole of 130.7. I've added those two values together and I get 350. When I take the difference of these two, I get my overall change in entropy at standard state, which is negative 120.8 joules per mole Kelvin. So this negative value right here means that this reaction leads to a decrease in entropy, a situation where things are much more organized. And we see that because at the beginning we start out with 2 reactants and we get 1 product. So we are going to a more organized state compared to our first example where we have a positive change in entropy at standard state, which means we are becoming more random. There is an increase in entropy. Now what I'd like you to do is do the following 2 examples on your own. So stop, pause the video, use the 2 previous examples to help you, write out your reaction, substitute your values in, and determine your overall change in entropy. Welcome back. Let's see how you did. Our change in entropy at the standard state for BeOH2 decomposing to BeO and H2O proceeds as following. I'm going to do my products minus my reactant. I substitute in my values for my gaseous water, my BeO, and my BeOH2. I multiply and add my values for my products together to get 202.6. I do the same thing for my reactant, which is 45.5. I take the difference, and the overall delta S here is 157.1 joules per mole Kelvin, which means this has a change in entropy that is positive. So the reaction becomes more random as it proceeds, which makes sense if I look at my overall reaction above, as we are going from one reactant to more than one product. Let's look at our second reaction. 2 moles of CH3OH plus 3 moles of oxygen yields 2 moles of CO2 and 4 moles of water. My change in entropy are my products minus my reactants. I substitute in my values for each. I find the difference between the values of the products minus the values of the reactants, and my end result is 87.4 joules per mole Kelvin. Again, a positive value, which means that as this reaction proceeds, there is an increase in entropy. Entropy changes in the surroundings. Surroundings serve as a large constant temperature heat source or heat sink, depending on the direction of energy flow from the system. The change in entropy of the surroundings will depend on how much heat is absorbed or given off by a system. So my change in entropy of my surroundings is equal to the change in heat over temperature, where delta H is my enthalpy change of the reaction and T represents my temperature in Kelvin. Let's look at an example. In the metallurgy of antimony, the pure metal is recovered via different reactions depending on the composition of the ore. For example, iron is used to reduce antimony in sulfide ores. So we have our reaction right here, and our overall delta H is negative 125 kilojoules. Carbon undergoes oxidation so that oxide ores are reduced. And again, we have our reaction and a delta H of 778 kilojoules. Calculate the change in entropy of the surroundings for each of these reactions at 25 degrees Celsius and 1 atmosphere. So the formula that we're going to use here is delta S of our surroundings is equal to change in enthalpy over the temperature. So in our first situation, from our first reaction, we're going to have negative 125 kilojoules over the change in heat. We need this to be in Kelvin, so we're converting 25 degrees Celsius into Kelvin, which we know is 298 K. We're going to find that to be negative 0.419 kilojoules per Kelvin. But in this case, because we're working with entropy and entropy is reported in joules, we're going to want to convert this over to joules. So that means it's 419 joules per Kelvin. Let's do the same thing for our second reaction. So we're going to have 778 kilojoules over 298 Kelvin. Again, we're going to divide this out, and as a result, initially we will get 2.61 kilojoules per Kelvin, but again, because we're working in entropy, we want to convert that over into joules. So our final answer here will be 2,610 joules per Kelvin. And this is an example of how to determine the energy changes in the surroundings.